All right, today we're going to pull back the curtain and really look inside the mind of an AI. So let's just jump right in with a massive question. We always hear that AI is trained on the internet, but what does that actually mean? Like, what really happens when you feed a model a data set so ridiculously huge you can't even wrap your head around it? Well, what you get is something kind of incredible, but also deeply, deeply flawed. Okay, so it all starts with what the AI eats, right? It's all about the training data. And for the big models today, like Llama 3, we're not just talking a big meal. We're talking about an absolutely colossal diet. Yeah, look at that number. 15 trillion tokens. It's a number that doesn't mean anything on its own, right? So let's try to put it in perspective. If you sat down and read one word every single second, no breaks, it would take you almost 500,000 years to finish. That is the raw material we're using to build an AI's brain.
So where in the world do you even get a mountain of text that big? Well, a huge chunk of it starts with a project called Common Crawl. You can think of it as this massive public archive of the internet, basically scraping billions of web pages for more than a decade now. And it is messy. It's a totally raw snapshot of the web. You get the good stuff, the bad stuff, and a whole lot of just total junk.
But here's the thing. You can't just take that raw, chaotic internet dump and feed it to an AI. No way. You've got to clean it up, refine it, and somehow turn all that chaos into a language that a machine can actually process.
And this part is absolutely critical. It's this super rigorous filtering pipeline. First, they use massive block lists to just get rid of all the obvious junk. Spam sites, malware, adult content. Then they take the raw web pages and strip out all the HTML code, just leaving the pure text behind. After that, they filter by language, right? So they might keep only pages that are, say, more than 65% English. And a really important final step, they scan everything to remove personally identifiable information, PII. It just goes to show you, with AI, it's not just about how much data you have. It's about the quality of that data.
All right, so once all the text is squeaky clean, it goes through this process called tokenization. And this is kind of the magic trick, right? This is where our human language gets translated into something a machine can actually compute.
See, when you and I look at text, we just see a continuous stream of letters and words. But in AI, it sees a sequence of tokens. A smart algorithm, like byte-pair encoding, breaks our text down into the most common chunks it can find. Sometimes that's a whole word, sometimes it's just a piece of a word. So a simple phrase like "Hello World" isn't seen as letters, it's seen as maybe two unique tokens, each with its own ID number. The model isn't reading words, it's just processing these numeric codes.
And this is where things get kind of mind-blowing. The model trains on this vast ocean of 15 trillion tokens, but its entire vocabulary, every single unique token it knows, is only about 100,000. That's it. It uses this relatively tiny, finite toolkit of word chunks to understand and reconstruct the entirety of human language. It's kind of wild when you think about it.
So if the AI isn't just, storing all 15 trillion tokens in some giant hard drive, what is it actually doing? Well, probably the best way to think about it is like a zip file.
Yeah, I love this idea. It really nails what an LLM is. It's not a database that you can query for perfect facts. It's a lossy compression, like a JPEG for text. It doesn't store every pixel perfectly. It just gets the general idea, the gist of the information.
And here's what that actually looks like in the real world. A 70 billion parameter model? That's a file that's about 140 gigabytes. That one file, small enough to fit on a thumb drive, is the compressed version of terabytes of internet data. And what's inside that file isn't facts, it's just statistical patterns. It's the probability of which token is most likely to come next.
So this leads to a really, really important distinction. The AI basically has two kinds of memory. You've got the parameters, that's the long-term memory, the big, vague, fuzzy zip file. But then you have the context window. Think of that as its working memory, like the RAM in your computer. It's much smaller, but anything you put in there for your current chat, it remembers perfectly. But, and this is key, the second you start a new chat, poof, it's all wiped clean.
And this weird combination of a huge, foggy long-term memory and a tiny, perfect short-term memory, well, it leads to some really, really strange results. Yeah, some folks in the field have started calling this the Swiss cheese problem. And it's perfect, right? You have a model that can write a beautiful poem or explain quantum mechanics, and then it will completely, utterly fail at a task that a kindergartner could do in 2 seconds. It's like this brilliant brain that's just riddled with these random, inexplicable holes.
And what's so strange about it is that the model has probably seen all of Wikipedia, like 10 times over during its training. It can memorize and spit back entire articles word for word. So we start to think it's perfect, that it knows everything. But those holes, they're still there. They're not bugs, they're just part of its fundamental design.
So why? Why does this happen? Let's look at a couple of super simple examples that really pull back the curtain on this.
Okay, here's a fun one. Go ask any of the big LLMs this question. It seems ridiculously easy, doesn't it? For a human, this takes, what, a second?
And yet, the AI will probably get it wrong. And the reason why goes right back to what we were talking about with tokens. It doesn't see the individual letters. It doesn't see an S, then a T, then an R. It just sees the token for straw and the token for berry. It thinks in chunks, not characters. So a task like counting letters is just totally alien to how its brain works.
All right, here's another one. This is so basic, it's almost silly. What's bigger, 9/11 or 9.9? I mean, come on, any machine should get this right.
But it might fail. And again, it's because it isn't actually doing math. It's just pattern matching based on its training. Think about it. On the internet, what is the token 9.11 most often associated with? A date. And 9.9? Maybe a price, like $9.99. It's weighing those powerful statistical connections from its training data, not actually comparing the numbers. The old context from the internet is literally polluting its ability to do basic logic.
So what's the big takeaway here? The bottom line is this: LLMs are not thinking machines, and they are not databases. They are just incredibly sophisticated pattern matchers. Their so-called knowledge is really just a foggy statistical map of how words relate to each other. And those bizarre Swiss cheese failures, they're not bugs that can be patched out. They are a fundamental, unavoidable consequence of the way these models are designed to see the world, token by token.
Honestly, understanding this really changes how you should use these tools. It stops being about asking, what do you know, and starts being about asking, what pattern are you most likely to complete for me? And that brings me to my question for you. Now that you understand why these weird failures happen, what's the strangest, most hilarious AI fail you've ever run into? Drop it in the comments. I'd love to see them.